Hi, today we are looking at section 5.5, which is conditional probability. So we'll look at some definitions, and then we'll look at some equations for it. So dependent events are events whose outcomes are affected by each other. So for example, two cards being drawn from a deck, the second outcome depends on the outcome of our first outcome. Now, conditional probability is the probability of an event occurring that another event has already occurred. Now, our notation for this is P bracket A vertical line of B. It's a probability that B will occur given that A has already occurred. If event B depends on event A occurring, then the probability of both events occurring is given by probability of A and B is equal to probability of A times our probability of B occurring given that A has already occurred. Example, you draw a card from a normal deck of cards, then draw a second card without returning the first. Are these events dependent or independent? So because we're not returning that card, the second event is going to depend on the first, because it's going to change up what cards are remaining in the deck and the number of cards left. So it is dependent. Now determine that both cards are diamonds. So probability of A and B is equal to probability of A times the probability of B given that A has already occurred. Now diamonds make up 1/4 of a deck. So therefore probability of our first card being a diamond is 1/4. Now, because we've pulled out that card and have not replaced it, our probability of a second one will not be 1/4. Instead, we start out with 13 diamonds. One has already been pulled out, so there's 12 diamonds remaining. And instead of pulling from 52 cards, we've pulled one card out, so there's 51 remaining cards. We multiply this, so this gives us 12 divided by 204. If we want to leave that as a fraction, we'll want to reduce that to lowest terms, which would be 1/17. Alternatively, we can write it as a percentage, which is roughly 6%. Next example, a computer manufacturer knows that in a box of 150 microchips, 3 of them will be defective. If you draw 2 microchips at random from a box, determine the probability that you draw A, 2 defective chips, B, 2 non-defective chips, C is exactly 1 defective chip. So for all of these are all dependent events. So we've got P, A, and B is equal to probability of A times the probability of B given that A has occurred. So if we're looking for defective chips, we've got 3 of them that are defective, and we're taking them out of a box of 150. We're going to be multiplying that then by probability of pulling another defective chip. So if we've already drawn one of our defective microchips out, that leaves us with just 2 microchips, and that's out of 149 because we've already pulled out one. So we're selecting from 149. So that would be probability of 0.027% chance of drawing 2 microchips are both defective. For B, 2 non-defective chips would be P, A, and B. So P of A times P of B given A has occurred. So if we have 3 defective ones, that means we have 147 that are working. And we're pulling from 150. Now for next one, we've already taken out one of 147 working. So we're down to 146 working. And we're down to 149 chips total. So that gives us 95.4%. Now, there's a couple ways to get this last one. If we didn't already have these calculations, I'll go over how to get exactly one defective chip. We're going to have to do 2 separate calculations. We're going to do one where our first chip pulled is defective and one where our second chip pulled is defective. So P, A, and B is equal to probability of A times the probability of B given A has occurred. So with this first one, this is if our first chip is defective, so 3 out of 150 times, we still have 147 chips that do work. So our second chip, because our first chip was defective, our second chip has to be working. So it's one of our working ones, and that's out of 149. So that gives us 1.97%. Now, the second part of it is if the first one we pull does work, but the second one does not. So if the first one works, then we're selecting one out of 147 that does work, times selecting 1 out of 149 that does, or one of 3 defective out of 149 chips, it does not work. And then we have to add up these 2 scenarios. So adding these gives us 3.95%. Now you'll notice that if you took, say, 100% and subtracted these 2 for A and B, it would give us this value here.